In the previous videos, we studied the graphs of sinusoid, sine and cosine, which are most important and also the most difficult. And then we studied the graphs of other trigonometric functions, tangent, and then cosecant, secant, cotangent functions, and then some composite trigonometric functions. Again, sine and cosines, sinusoid functions played a great role there, like axis of oscillation, envelopes, beads, things like those. But then again, those are interesting and they have a lot of nice applications, especially in physics and engineering. But for further mathematics, especially to solve some equations and then do some algebra, we need inverse functions. But then again, there's a bit of a problem. Trigonometric functions are generally not one-to-one, they're highly not one-to-one. So how do we make those kind of functions into a one-to-one function and take the inverse function? What kind of restriction is necessary for that? Well, this is what we need for sine function. Here we have a graph of a sine function going up and down and up and down. And what we do is to restrict the domain from negative pi over 2 to pi over 2. In this domain, we have the range negative 1 to positive 1, and the graph of the sine function in this domain will turn out to be this thick blue curve in this graph here. In this region, we have one-to-one, so we can consider the inverse function. And that inverse function is called inverse sine function or arcsine function. Now, what does an inverse function do? Inverse functions flips x and y basically. X goes to y, y goes to x. And consequently, domain becomes the range, range becomes the domain. So domain of the inverse function is negative 1 to positive 1. Range is negative pi over 2 to positive pi over 2. The graph of the inverse function is symmetric with respect to the principal diagonal y equals to x. So we have that red graph, and that is the graph of the arcsine function. So if you have any number between negative 1 and positive 1, and you can use your calculator to find out an arcsine, and you can find out the angle whose sine value is that given number. But then again, that solution is not going to be unique. We're going to discuss that later. Now let's move on to arc cosine function. And here it is. Graph of a cosine function is given here in blue. And we have to restrict its domain so that it is one-to-one. And that domain is 0 to pi. And in 0 to pi, cosine function is one-to-one. And the range is negative 1 to positive 1. Now, if we take the inverse function, domain becomes range, range becomes domain. So domain of the inverse function is negative 1 to positive 1, and the range is from 0 to pi. And that inverse function is called inverse cosine function or arc cosine function. And it's the red graph. As you can see, this red graph, the graph of the arc cosine function, is symmetric to the graph of the cosine function, the blue one, with respect to the principal diagonal y equals to x, this purple dotted line. How about the tangent function? Well, tangent function is actually a bit easier. The natural domain, negative pi over 2 to pi over 2, is generating this thick blue curve, thick blue curve here, y equals the tangent of x, and that is one-to-one. So by taking the inverse of that, we get inverse tangent or arctangent function. And because this tangent function goes from negative infinity to positive infinity, the domain of the inverse function is negative infinity to positive infinity too. And that's interesting. The other inverse trig functions, arcsine and arccosine, had finite domains. But arctangent, on the other hand, has unbounded domain. Actually, the domain of the arctangent function is entire real numbers, negative infinity to positive infinity. The range, on the other hand, is from negative pi over 2 to pi over 2. And instead of those two vertical asymptotes of this tangent function, x equals negative pi over 2 to x equals a positive pi over 2, we end up with a couple of horizontal asymptotes, y equals negative pi over 2 and y equals positive pi over 2 for arctangent function. It's an interesting quantity there. It'll turn out that among those three inverse trigonometric functions, arctangent will turn out to be the most important in calculus. Here in trigonometry, arcsine and arccosine are equally as important or more. What kind of problems are there about those inverse trigonometric functions? Oh, stupid problem. Sine of arctangent of 1. Well, we are living in the 21st century, so use your calculator and calculate it, and then you're going to be done. But if you really want to do it without calculator, arctangent of 1 is pi over 4, so this is nothing more than sine of pi over 4. How about the next one? Cosine of twice of arcsine of negative 1/2. Again, the same comment as before. Pick up your calculator and then click, and then you're going to get an answer. However, suppose that you do not have calculator, or if you're unwilling to use it, well, you can use known triangle. Arcsine of negative 1/2. Well, what kind of angle gives you sine as negative 1/2? It's going to be 1 squared root of 3, 2 triangle. You're going to get negative pi over 6. Twice of that will be negative pi over 3. Cosine of negative pi over 3 is 1/2. But then again, you can use calculator. Here I'm using Mathematica. Here are some further values here, but then again, well, again, use 21st century mathematics. Use calculator or use computer algebra system. You're going to get an answer. Arcsine over arccosine, if you want something like this, well, copy and paste and then run it, and then we have an answer. And that's probably the best way to answer that kind of problem. It is difficult to, if you do not have Mathematica, then you can do the same thing in Wolfram Alpha. Now, what's the point of studying inverse trigonometric function if all these are just punching the calculator? Well, here is the big reason why inverse trigonometric functions are so important. They are used in solving equations. All equations are important. For example, if you're interested in solving a sine of x equals m, m is too close to 0. Let's run it again. This program is a little bit randomized. Okay, this is good. M value is a little bigger than 0.6, it appears. And if you take arcsine of m, then you're going to get this blue point, solid blue point on the standard curve, standard domain between negative pi over 2 to pi over 2. The solid, the thick solid part of the sine curve. But that's not enough. By the symmetry of the sine function, pi minus of that is automatically an answer. And that one is represented by solid red dot in this curve. And then, of course, we have those two answers, arcsine and pi minus arcsine. Now what do we have? Plus 2k pi. Plus 2k pi, well, that's coming from the period. So the pair, the solid blue and solid red pair, is reproduced in the next period, this blue and red. And then if you move 2 pi to the left-hand side, we have another pair, blue and red. And of course, if we simply go on for next period, and so on, we'll have another pair, another pair, another pair like that. You'll have blue-red, another blue-red, another blue-red, another blue-red, kind of like this. And the solid blue came from arcsine computation, and the solid red came from pi minus of that. So simply calculating the arcsine is not enough. You're only going to get these blue solutions. How about arc cosine function or solving a cosine equation? Well, okay, let's go with that. If you take arc cosine, you're going to get this solid blue point on the standard domain where we have solid blue curve. But then again, because cosine function is even, negative of arc cosine is automatically an answer. And that one is the solid red one you see here in this picture down below. And then we got those pair, blue and red, solid blue and solid red. You can always add 2 pi to get the next pair, blue-red, and then another 2 pi to get another pair, blue-red, and the pattern will continue. Another pair, another pair, another pair. Let me emphasize again. Solid blue came from arc cosine. Negative of that gave you solid red. And the other red-blue, those pairs are coming from adding 2 pi's, the period. How about arctangent? Actually, that's much easier because the period of tangent function is pi, so you don't really have to meddle about those pairs. All you have to do is add pi, another pi, another pi. You can cover everything, like in this picture. I guess we have sufficient time for an exercise, so let's go ahead and solve a trigonometric equation like this. 3 sine of x plus 1 is equal to 2. Let's solve that. We have sine of x is equal to 1/3. So what do we have? Arc sine of 1/3, excuse me. And then pi minus of that. And then of course, adding 2 pi's, 2k pi's, we'll have the full solution. As a matter of fact, here is a visualization. And arc sine of 1/3 is solid blue. Pi minus that is solid red. And this curve. And then adding 2 pi, we have another pair, blue-red with those hollow. And then add another 2 pi, we are going to get another pair, but that's more to the right. And of course, if you subtract 2 pi, we can go to the left, and then we are going to get a pair of solutions. Of course, there are infinitely many solutions out there because this k can be arbitrary integer. How about the next problem here? Cosine function. Okay, solve it using algebraic technique. Cosine is -3/4, and plus or minus arc cosine of -3/4 will give you solutions, blue and red. And then 2k pi, add 2 pi, and then you have another pair, blue-red. And another 2 pi, we have another pair. Add another 2 pi, we'll have another pair, and so on and so forth. Same to the left-hand side as well. Time for tangent equation. Okay, here is tangent equation. And what do we get? 2 sine of x plus cosine of x is equal to 0. And 2 sine of x is negative cosine of x here. And divide both of them by cosine, then we have tangent is -3/2. So tangent is -3/2, so we have x is arctangent of -3/2. And arctangent function, tangent function has period pi. So one solution from arctangent, which is solid blue here. And then we have k pi plus k pi, so we have all the period. And adding pi, we have another solution in the left. And then adding another pi, we have another solution further to the right. Okay, we do not have enough time to talk about trig inequalities. So let me just show you a picture and then leave those as challenge to you. How to solve an inequality? Solve an equation and then use graphs. Here,